The universe at its strangest. For most of human history, the universe appeared to follow a set of simple, reliable rules. If you throw a stone into the air, it will arc upward and fall back to the ground. If you push a cart, it will roll forward until friction slows it down. The world behaves like a giant machine, its movements predictable and orderly. For centuries, this view of reality shaped the way scientists understood the cosmos. In the 17th century, physicists like Isaac Newton formalized these ideas into mathematical laws. Newton's equations described motion, gravity, and forces with remarkable precision. With them, scientists could predict the motion of planets, the trajectory of cannonballs, and the behavior of falling objects. The universe, it seemed, operated like a perfectly designed clock. If you knew the position and motion of every object at a given moment, you could theoretically calculate the entire future of the cosmos. This vision of reality is often called the classical universe, a world governed by cause and effect, where every event has a clear explanation, and every outcome can be predicted if enough information is known. For centuries, this framework worked extraordinarily well. It built bridges, powered engines, and sent ships across oceans. It allowed humanity to calculate eclipses centuries in advance and understand the mechanics of the solar system. But as the 19th century turned into the 20th, scientists began to peer deeper into the structure of matter itself. And what they found began to unravel the comfortable certainty of the classical world. The first cracks appeared when researchers started studying the behavior of light and atoms. Light had long been understood as a wave, a smooth, continuous ripple traveling through space, much like waves on water. But experiments revealed something strange. Under certain conditions, light behaved not like a wave at all, but like a stream of tiny particles. In 1905, Albert Einstein proposed that light could be thought of as packets of energy called photons. This idea helped explain the photoelectric effect, where light striking a metal surface can eject electrons. The discovery was revolutionary. Light was both a wave and a particle. This dual nature, known as wave-particle duality, was deeply unsettling. In the classical world, objects behaved one way or another. Something could be a wave or a particle, but not both at the same time. Yet at the microscopic level, nature refused to follow these tidy categories. Even stranger discoveries followed. When scientists began experimenting with individual particles like electrons, they found that these particles also behaved like waves. In experiments such as the double-slit experiment, electrons fired toward a barrier with two narrow openings produced interference patterns, ripples characteristic of waves. But when detectors were used to observe which slit the electron passed through, the pattern changed completely. The electron suddenly behaved like a particle again. It was as if the act of observing the system altered its behavior. These experiments forced physicists to confront an unsettling truth. The universe, at the smallest scales, does not behave like the predictable machine described by classical physics. Instead, it operates according to a set of rules that seem almost alien to our everyday intuition. In the classical universe, if you know the starting conditions of a system, you can predict exactly what will happen next. A ball thrown into the air will follow a specific path determined by gravity and motion. But in the quantum world, certainty disappears. Instead of precise outcomes, physicists can only calculate probabilities. At the heart of quantum mechanics lies a simple but profound idea. Particles do not have definite positions or states, until they are measured. Before observation, they exist in a range of possible outcomes simultaneously, described mathematically by a wave function, a kind of probability cloud representing where the particle might be found. This means that when scientists study the behavior of an electron around an atom, they cannot say exactly where the electron is at any given moment. They can only describe a region where it is likely to appear. The shift from certainty to probability was one of the most dramatic revolutions in the history of science. Reality itself seemed to become fuzzy, indeterminate, and strangely dependent on measurement. One of the central figures in this transformation was Werner Heisenberg, who formulated the uncertainty principle. This principle states that certain properties of particles, such as their position and momentum, cannot both be known precisely at the same time. The more accurately you measure one, the less precisely you can know the other. This was not merely a limitation of measurement tools. It appeared to be a fundamental property of nature itself. The implication was staggering. At the deepest level of reality, the universe is not completely knowable. It is governed by uncertainty. For many physicists, this conclusion was deeply uncomfortable. Even Einstein, whose work helped launch quantum theory, struggled with its implications. He famously resisted the idea that chance governed the universe, remarking that God does not play dice. Yet experiment after experiment confirmed the predictions of quantum mechanics with extraordinary accuracy. The strange mathematics describing probabilities, wave functions, and uncertainty turned out to be one of the most successful scientific theories ever developed. The world we experience, the solid ground beneath our feet, the predictable motion of planets and objects, emerges from this deeper quantum reality. At large scales, the strange behavior of particles averages out, producing the stable universe we are familiar with. But beneath that stability lies a realm of constant uncertainty, where particles flicker between possibilities and reality itself, seems to hover in a cloud of probability. This discovery transformed our understanding of existence. The universe was no longer a perfectly predictable machine. It was something far stranger, a dynamic system built on uncertainty, chance, and hidden possibilities. And this was only the beginning. As scientists continued to explore the quantum world, they uncovered phenomena even more bewildering. Particles that could exist in multiple states at once, connections that spanned vast distances instantly, and experiments suggesting that observation itself might shape reality. The deeper we looked into the fabric of the universe, the stranger it became. The comfortable certainty of the classical world had been replaced by something far more mysterious. A cosmos where the smallest pieces of reality behave in ways that challenge logic, intuition, and perhaps even the nature of reality itself. And in that strange quantum realm, the rules we take for granted may not apply at all. The particle that lives in two places. If the first chapter revealed that the universe is stranger than we once believed, the next discovery pushed that strangeness even further. It suggested that at the smallest scales of reality, particles do not simply occupy one place at one time. Instead, they can exist in many possible states simultaneously. This idea lies at the heart of one of the most fundamental concepts in quantum physics: quantum superposition. To understand why this idea is so unusual, we must first consider how objects behave in the everyday world. If you place a coin on a table, it will show either heads or tails. If a light switch is flipped, it is either on or off. In the classical universe described by Isaac Newton, Systems exist in clearly defined states. An object is here or there, moving or stationary, one thing or another. But in the quantum world, nature does not seem to follow these rules. When physicists examine extremely small particles, such as electrons, photons, or atoms, they find that these objects do not behave like tiny solid balls moving along definite paths. Instead, they behave more like waves of possibility. A particle can exist in several potential states at the same time, each with a certain probability. Before measurement occurs, the particle is not simply hidden in one location waiting to be discovered. According to quantum theory, it genuinely occupies a combination of multiple states simultaneously. This strange condition is what physicists call superposition. One of the best ways to visualize this comes from a famous thought experiment proposed in 1935 by the Austrian physicist Erwin Schrödinger. Known as Schrödinger's cat, the scenario was originally designed to highlight how bizarre quantum theory becomes when applied to everyday objects. Imagine a sealed box containing a cat, a radioactive atom, a Geiger counter, and a small vial of poison. The setup is arranged so that if the radioactive atom decays, the detector triggers the release of the poison, killing the cat. If the atom does not decay, the cat remains alive. Radioactive decay is a quantum process. It occurs randomly and cannot be predicted with certainty. According to the mathematics of quantum mechanics, before we open the box and observe the system, the atom exists in a superposition of two states, decayed and not decayed. If the atom is in both states at once, the consequences become unsettling. In the logic of quantum mechanics, the entire system inside the box, the detector, the poison, and the cat, must also exist in a superposition. Until the box is opened and the system is observed, the cat would theoretically be both alive and dead at the same time. Of course, Schrödinger did not believe cats actually exist in such a bizarre condition. His thought experiment was meant to expose the apparent absurdity of applying quantum rules to the everyday world. Yet over the decades, experiments have repeatedly confirmed that superposition is not just a mathematical trick. It is a real feature of nature. At the microscopic scale, particles truly can exist in multiple states simultaneously. To understand how this works, physicists often describe particles using something called a wave function. Rather than representing a particle as a tiny object with a precise position, the wave function describes a probability distribution, a cloud of possible locations where the particle might appear. An electron orbiting an atom, for example, does not travel along a fixed path like a planet circling a star. Instead, it exists as a fuzzy region of probability surrounding the atomic nucleus. Within this region, the electron could be found in many different places, all at once. Only when a measurement is made does the electron appear at a single, definite location. This process is often referred to as wave function collapse, the moment when the many possibilities contained in the quantum system resolve into one observable outcome. The role of observation in this process has puzzled physicists for more than a century. Does the act of measurement actually force the particle to choose a single state? Or does the particle always have a definite state that simply becomes revealed when we observe it? Quantum mechanics itself does not provide a clear answer. It only tells us how to calculate probabilities and predict outcomes. One of the most famous experiments demonstrating superposition is the double-slit experiment, which reveals how particles behave when not directly observed. In this experiment, particles such as electrons or photons are fired toward a barrier containing two narrow slits. If particles behaved like tiny bullets, they would pass through one slit or the other, creating two simple bands on a detector screen behind the barrier. Instead, something remarkable happens. When particles are not observed, they produce an interference pattern, a series of bright and dark stripes that can only occur if the particles behave like waves passing through both slits simultaneously. It appears as though each particle travels through both openings at the same time, interfering with itself as if it were a wave spread across multiple paths. Yet when detectors are placed at the slits to observe which path the particle takes, the interference pattern disappears. The particle suddenly behaves like a classical object again, choosing one slit or the other. The act of measurement changes the outcome. Experiments like this have been performed countless times with increasing levels of sophistication. Researchers have even demonstrated superposition with larger objects, including entire molecules made up of hundreds of atoms. Each experiment confirms the same unsettling conclusion. The quantum world is fundamentally different from the reality we experience at larger scales. Particles do not possess definite properties until they are measured. Instead, they exist in a spectrum of possibilities, described by probabilities rather than certainties. This realization reshapes our understanding of what matter actually is. The solid objects we see around us, the ground, the air, our own bodies, are built from particles that, at the deepest level, behave more like waves of potential than physical objects. The stable world we experience emerges from the collective behavior of these quantum systems, where probabilities combine and average out to produce the appearance of certainty. But beneath that stability lies something profoundly strange. At the most fundamental level, reality is not a collection of solid things occupying definite places in space. It is a shifting landscape of probabilities, where particles can exist in multiple states, follow multiple paths, and only become definite when observed. The universe, it seems, does not settle on a single version of events until we look. And if particles can exist in multiple states at once, the question naturally arises: what happens when two particles become connected across space itself? The answer leads to one of the most mysterious phenomena in all of physics: quantum entanglement. It is as if the particles remain connected by an invisible thread, even when separated by vast distances. To grasp how strange this is, consider an example often used by physicists. Imagine two entangled particles that have opposite spins. Spin is a quantum property that can be measured as either up or down. When the particles are created, neither particle has a definite spin direction. Instead, the system exists in a superposition where both possibilities are present. But the moment one particle is measured, its spin becomes definite. If the first particle is found to be spin up, the second particle will immediately be spin down. If the first is measured as spin down, the other becomes spin up. This would not be surprising if the particles were still close together, but entangled particles can be separated by enormous distances, across laboratories, across continents, even potentially across astronomical scales. Yet the correlation between them remains perfect. No matter how far apart they are, measuring one instantly determines the state of the other. This strange connection troubled many physicists when it was first proposed. Among the skeptics was Albert Einstein, who was deeply uneasy about the implications of quantum mechanics. Einstein believed that the universe should obey certain fundamental principles, including the idea that information cannot travel faster than light. This limit, central to the theory of relativity, ensures that cause and effect remain consistent across the universe. But entanglement appeared to violate that rule. If measuring one particle instantly influences another particle far away, it seems as though some form of information is traveling faster than light. Einstein famously dismissed the idea as spooky action at a distance. He suspected that quantum mechanics was incomplete, that hidden variables, not yet discovered, would eventually explain the strange correlations without violating the laws of physics. For decades, the question remained unresolved. Then, in the 1960s, a physicist named John Stuart Bell proposed a way to test whether hidden variables could explain quantum entanglement. Bell developed a mathematical framework, now known as Bell's theorem, that allowed physicists to distinguish between the predictions of classical hidden variable theories and those of quantum mechanics. If Einstein was right, experiments should follow the rules predicted by hidden variables. But if quantum mechanics was correct, the results would violate those classical limits. Over the following decades, physicists conducted increasingly precise tests of Bell's theorem. One of the most famous experimental confirmations came from the work of Alan Aspect in the early 1980s. Aspect and his team created pairs of entangled photons and measured their properties after sending them in opposite directions. The results were clear. The correlations between the photons violated Bell's inequality exactly as quantum mechanics predicted. The particles behaved as though they remained connected, even when separated by large distances. Since then, many experiments around the world have confirmed entanglement with increasing precision. Researchers have entangled photons, electrons, atoms, and even small groups of molecules. In some cases, entangled particles have been separated by kilometers of optical fiber or transmitted between ground stations and satellites orbiting the Earth. In 2017, a Chinese satellite named Micius successfully distributed entangled photons between stations more than 1,000 kilometers apart, demonstrating that entanglement can persist across extraordinary distances. The phenomenon is no longer a theoretical curiosity. It has become a powerful tool in emerging technologies, such as quantum cryptography and quantum computing, where entangled particles can encode and process information in ways that classical systems cannot. Yet despite these practical applications, the deeper meaning of entanglement remains mysterious. How can two particles remain connected across space? What mechanism allows them to share information instantly without violating the speed of light? One important clarification is that entanglement does not allow messages to be sent faster than light. While the measurement outcomes are correlated, scientists cannot control the result of a quantum measurement. This means the phenomenon cannot be used to transmit usable information instantaneously. Even so, the existence of these instantaneous correlations challenges our most basic assumptions about the nature of reality. In the classical view of the universe, objects are independent entities. They occupy specific positions in space, and interactions between them occur through forces that propagate over time. Space acts as a stage upon which events unfold, separating objects and defining their relationships. Quantum entanglement suggests that this picture may be incomplete. At the deepest level of reality, particles that interact can become part of a single, inseparable system, even when separated by vast distances. Their properties are not entirely independent. Instead, they are defined together as part of a larger quantum state. This idea has led some physicists to propose that space itself might not be as fundamental as we once thought. The connections created by entanglement hint at a deeper layer of reality, where relationships between particles exist prior to the structure of space and time. In this view, the universe might be less like a collection of separate objects scattered through space, and more like a vast network of interconnected information. Distance, in this deeper framework, may not represent a true separation at all. The philosopher and physicist David Bohm once described the universe as an undivided whole, where what appears separate in our everyday experience may actually be deeply connected beneath the surface. Quantum entanglement offers a glimpse of this possibility. Two particles created together remain linked across space, responding to measurements in ways that defy classical explanation. The connection does not weaken with distance. It does not require a signal to travel between them. It simply exists, embedded in the structure of quantum reality. The deeper scientists explore the quantum world, the more they discover that our everyday assumptions about space, separation, and independence may only be approximations, useful for navigating daily life, but incomplete descriptions of the underlying universe. Reality, it seems, may be woven together by connections far stranger than we ever imagined. And if particles can share states across vast distances instantly, another unsettling question begins to emerge. If the universe is built from probabilities, superpositions, and entangled systems, then what role does observation itself play in shaping reality? That question leads to one of the most profound mysteries in all of physics. Whether the act of observing the universe might help determine the reality we experience. Does reality even exist without us? By the time physicists uncovered superposition and quantum entanglement, the picture of reality had already become deeply unsettling. Particles could exist in multiple states at once. Objects separated by vast distances could remain mysteriously connected. The smallest building blocks of nature behaved not like tiny solid objects, but like shifting clouds of probability. But perhaps the most disturbing question, raised by quantum mechanics, concerns something even more fundamental. What role does observation play in shaping reality itself? In the classical universe imagined by Isaac Newton, the answer seemed obvious. The world exists independently of us. Mountains, planets, and atoms continue their motion whether or not anyone is watching. Observing the universe simply reveals what is already there. Quantum physics challenges this assumption. At the heart of the theory lies a mathematical object known as the wave function, a description of all the possible states a quantum system can occupy. Before measurement occurs, a particle does not appear to exist in one definite state. Instead, it exists in a superposition of possibilities, each represented within the wave function. But when a measurement is made, something remarkable happens. The wave function collapses. The range of possibilities suddenly resolves into a single, definite outcome. An electron that existed as a probability cloud appears at one specific location. A particle that could have been spin up or spin down becomes one or the other. The moment of observation seems to force the universe to make a choice. This phenomenon is often called the observer effect, and it raises one of the deepest questions in physics. What exactly counts as an observation? Does the collapse occur when a human being looks at a measurement device? Does it happen when a detector interacts with a particle? Or does it occur whenever a quantum system interacts with its environment? Quantum mechanics itself does not clearly answer this question. early pioneers of the theory were deeply puzzled by the implications. Among them was Niels Bohr, who helped develop what became known as the Copenhagen interpretation. According to this view, the wave function does not represent a physical object, but rather our knowledge of a system. Measurement updates that knowledge, producing the definite outcomes we observe. In this interpretation, the act of measurement plays a fundamental role in defining physical reality. But not everyone found this explanation satisfying. Some physicists wondered whether consciousness itself might be involved in the process, or if the wave function collapses only when an observation occurs. Could the observer, the conscious mind, be playing a direct role in shaping the outcome? The idea has fascinated philosophers and scientists alike. Could reality remain in a state of possibility until it is perceived? Does the universe require observers to bring definite events into existence? While intriguing, most physicists today are cautious about linking quantum mechanics directly to consciousness. Experiments suggest that wave function collapse, or something very much like it, can occur when particles interact with measuring devices or with their surrounding environment, long before any human observer becomes involved. Even so, the observer problem remains one of the most debated questions in physics. If observation does not require consciousness, then what mechanism determines how the many possible states of a quantum system become a single outcome? One of the most radical attempts to answer this question emerged in 1957, when the physicist Hugh Everett III proposed what is now known as the many worlds interpretation. Everett suggested that the wave function never collapses at all. Instead, every possible outcome of a quantum event actually occurs, but in separate branches of reality. When a measurement is made, the universe splits into multiple versions, each representing one possible result. In one branch, the electron appears here. In another, it appears somewhere else. In one universe, the particle spins up. In another, it spins down. All possibilities exist simultaneously, but in separate versions of reality. This interpretation eliminates the need for wave function collapse entirely. The quantum probabilities simply represent the different branches into which the universe divides. The implications are staggering. Every quantum event could create new branches of reality, producing an ever-expanding multiverse of parallel worlds. In some of those worlds, events unfold exactly as we experience them. In others, different outcomes occur, different histories, different choices, different futures. The idea connects quantum mechanics to the concept of multiverse, suggesting that reality may be far larger and more diverse than our single observable universe. Whether the many worlds interpretation is correct remains an open question. Yet, it highlights just how profoundly quantum theory challenges our understanding of existence. The strangeness does not stop there. Quantum mechanics also forces us to rethink the nature of time. In everyday experience, time seems to flow smoothly from past to future. Causes precede effects, and events unfold in a clear sequence. But the equations describing quantum systems often treat time in ways that do not fully match this intuitive picture. Some interpretations suggest that quantum processes may involve correlations that stretch across time, linking events in ways that blur the distinction between cause and effect. Others propose that time itself might emerge from deeper quantum relationships, rather than existing as a fundamental backdrop for events. The deeper physicists probe into quantum theory, the more it seems that many of our most basic concepts, space, time, causality, and even reality itself, may not be as fundamental as we once believed. Instead, the universe may be built from something more abstract, a web of probabilities and relationships from which the solid world gradually emerges. In this view, the familiar reality we experience every day is not the deepest layer of existence. It is an emergent phenomenon arising from countless quantum interactions that average out to produce stable objects and predictable laws. The table in front of you appears solid, but it is made almost entirely of empty space, filled with particles whose exact positions are never fully certain. Your own body, composed of trillions of atoms, exists because the strange probabilities of quantum mechanics combine in ways that create the illusion of stability. Beneath that illusion lies a universe that is constantly fluctuating, branching and evolving in ways that challenge our deepest intuitions. And perhaps the most remarkable thing is that these strange quantum laws do not merely describe a hidden microscopic realm. They are the foundation of everything that exists. Every star in the sky, every atom in your body, every thought passing through your mind emerges from the same strange quantum rules discovered more than a century ago. The deeper we look, the less the universe resembles the predictable machine once imagined by classical physics. Instead, it appears more like a vast landscape of possibilities, where certainty is rare and probability governs the unfolding of events, which leaves us with a final, unsettling thought. If reality is built from probabilities rather than fixed outcomes, if particles exist in many possible states until measured, if entire universes might branch from quantum events, then the world we experience may be only one version of what reality could be. The universe, at its deepest level, may not be a single story unfolding in a fixed way. It may be something far richer and stranger, a cosmic tapestry woven from possibilities. And the reality we observe may be just one thread among countless others.